Welcome to video 6 of the regression analysis course. Okay, so now we all know what the linear regression model is. Before I jump into anything new, I just want you all to quickly note something important. There are multiple names for the same variable, and that can be sometimes very confusing. So let's clear that up first. The dependent variable, which is the effect we are trying to understand or predict, it has several other names as well: response, outcome, or output. The independent variables, these are the causes or factors that influence the dependent variable. And it has also other names such as predictors, explanatory variables, or sometimes even features. All right, with that out of the way, let me talk about something else. Given any p predictors and n observation, the linear model for any ith observation yi would be equals to beta naught plus beta 1 xi1 plus beta 2 xi2, so on and so forth, plus beta p xip plus epsilon I. And since we have n observation, we have this for all I equals to 1 to n. And then we made some assumptions on this error term that epsilon I is normally distributed with mean 0 and variance sigma square. This is true for all I from 1 to n. And also we know that EI and EJ are independent and identically distributed. And under this assumption, we have that expected value of yi is equals to beta naught plus beta 1 x1 plus beta 2 x2 till beta p xp. Now, whenever we have this linear regression model, here y is the dependent variable. Again, it has other names as well. It could be outcome, response, output, so on and so forth. And when we say yi, it means the value of the dependent for the ith observation. And we have independent variables present in the model. So again, it has other names: predictors, explanatory variable, features. All these x1, x2, x3, so on and so forth till xp are the independent variables present in the model. And other than these two variables, we have betas present in the model. These betas are the unknown quantity, and we call these unknown quantities as parameters. And these are also called regression coefficients. Beta naught in particular is called intercept. It is the beta which do not have any independent variable in multiplication or division. And this beta, particularly this beta naught, is called intercept. And all the other betas that have independent variable in multiplication with it are called slope coefficient. Here beta 1, beta 2 till beta p are slope coefficient. And in this course, we will learn how to estimate these regression coefficient based on the sample data. Because if we look at the equation and given any data set, we will have the value of the dependent variable for all the n observation. We will have the value of these p independent variable for all the n observations. So the only unknown quantity over here is the beta matrix, the coefficients we have for all the independent variables. So our goal is to learn how to estimate the value of these unknown quantities, these parameters or regression coefficients based on the data set we have. Before we estimate the value of the regression coefficient when we have p predictors in the model, we'll start with the simplest regression model. What could that look like? Well, imagine a case where you do not have any predictors at all in your model. That's right. No independent variables at all, only dependent variable. So we do not have any x in the model. When we remove all the x1, x2, x3, so on and so forth till xp from the model, the only thing left in the model is beta naught, which is the intercept, and the error term epsilon I. So we have only dependent variable yi, and it is equals to beta naught plus epsilon I. And if we look at this equation closely, we would have the value of the dependent variable for all the n observations, and the only unknown quantity over here is beta naught, which is the regression coefficient. which is the parameter over here. We have only one parameter, only one regression coefficient. And then the leftover term, which is the error term, is the uncertainty present in the model. Let me show you this with a quick example. Let's assume that you are a teacher or a very great conscious student who wants to understand the relationship between how much a student studies and how well they perform on an exam. In academic settings, exam scores are often influenced by the number of hours spent studying. Most of the time, the more hours a student studies, the higher their exam score tends to be. As the teacher or student, you would like to develop a model that allows you to predict the exam score based on how many hours a student studies. Therefore, one semester you collect data from 6 students after an exam. Unfortunately, when you start analyzing your data, you realize that you only recorded the exam scores and completely forgot to record how many hours each student studied. So, this is the only data you have available. You have the exam score of 6 students. This student number over here does not really affect the exam score in any way. It just means that one of the students in your data has exam score 65. The other student has exam score 68. That's it. It does not really affect the exam score. So only thing you have in the data set is the dependent variable, exam score, and there is no other variable present in this data set, and there is no other information left to you. There is no independent variable present in this data set. So what can we do in this case? Can we still build a model with just this one dependent variable present in the model? The answer is yes. And this leads us to the most simplest form of regression model, also known as the mean model or the intercept-only model. So this mean model or the intercept-only model are the other names for the null model, which is when you do not have any independent variable present in your data set. So the only thing you have is one variable, which is the dependent variable. We have no independent variables present in the model. So the model would just look like y is equals to beta naught plus epsilon. Only intercept would be there. There would be no slope coefficient because there is no independent variable. So all we have is an intercept beta naught, an error term epsilon. And now, if I ask you what would be the best prediction for anything in the future using this model, the best prediction would be the best estimate of beta naught such that the error is as small as possible. And that's exactly the idea. Let's try to understand this with the same example. We all agree that the exam score usually depends on how many hours you studied for the exam. Suppose you are a teacher and you collect data from 6 students, both their exam scores and the number of hours they studied. Because you wanted to build a model that says if someone studies for this many hours, I can predict their exam score. But let's say when you actually sit down to analyze the data, the file with the study hours somehow got deleted or lost. So now you're only left with the exam scores, the dependent variable, and no independent variable, no predictor. So all you have is this data. No independent variables, no study hours, no features, nothing. Now, if I ask you a question, what would be the exam score of the 7th student? What's the best guess you can make? You'll probably look at the exam score of all these 6 students and say, I don't have any other information. So maybe I'll just take the average of all the exam scores I already have. Exactly. That's the most reasonable and safest guess you can make when you have no other input to base your predictions on. The average becomes your best estimate because it's the one value that's kind of in the middle of all the other values you have in the data sets, it's the closest overall to all the data points. Intuitively, the average would become the best estimate if we have only dependent variable present in the data set. Let's try to visualize whatever we have talked about. We have the exam score of some student, one, which is 65, exam score of second student 68, so on and so forth. If we plot all these And if we plot these values, this is what we'll get. The exam score of student 1 is 65. The exam score of second student is 68, so on and so forth. So the exam score is the dependent variable. And on the x-axis, we have student number. And again, the student number does not affect the exam score. It just represents that one of the students has 65 points in the exam, the second student has 68 points in the exam, so on and so forth. And the best guess we have, given only dependent variable in the data set, is the mean of all the observed values, the average of all the data points, which is 75. So we have observed values. What are observed values? The actual data points we have. These blue dots over here, these represents the actual data points. The first blue data point means the exam score of the first student. The second blue dot represents the exam score of the second student, and we call them observed value. The value of the dependent variable for the first observation, observed value, the actual data point we have. And once the average line is drawn, that line also represents the predicted value for each observations. Why? Because in the absence of any independent variable, the average becomes our best estimate for every point. And so the average line depicts the predicted value for each observation. So we started with this data set, and the average of all the exam scores over here is equals to 75. So we add 65, 68, 72, 78, 82, 85 divided by the number of observations, which is 6 over here. And we get 75. So 75 is the predicted value for each observation, and that's the best we can do, because average is the point that minimizes the total deviation from all the values. So that's the best guess we have when we only have one variable present in the data set. If we look at this table properly, we see that the exam score of the first student, which we also call as observed value, the actual value of the exam score of the first student is 65. But what we have predicted is 75. So there is 10 points difference between the observed and the predicted value. Similarly, for the second observation, the exam score of the second student is 68, but what we have predicted is again 75. And again, there is some sort of difference between the observed value and predicted value. And in each observation, we can see that the observed value is not same as the predicted value. There is some sort of difference in each observation between the observed and the predicted value. Now, this difference between the observed and the predicted value is called as error or residual. Let's try to visualize it again. So we have the blue dots that represents the observed value, and then we have the average line that depicts the predicted value, and the difference between the observed and the predicted value is what we call as error or residual. And here this black line represents the error for each observation. Let's try to calculate the error for each observation. For the first observation, the exam score of the first student is 65. What we predicted is 75. So the error is the difference between the observed and the predicted. Error is defined as the observed minus the predicted value, which will be negative 10, because 65 minus 75 is negative 10. Similarly, the error for the second observation would be 68 minus 75, which is negative 7. And this is how we find the error for each student. We look at the difference between their actual score and the average observed value, actual score, and the predicted value, which is the average. Awesome. So we have this table. If you sum up all these errors, observed value minus predicted values, you'll find that they add up to 0. Does that mean that there is no error in the model? Not at all. That's a problem. From the first observation, we have -10 as error. From the second observation, we have -7. So we have error from each observation, but then adding it up gives us 0. Doesn't make a sense. And it is happening probably because we have negative and positive values of error. And the problem is that the positive and negative differences cancel each other out. So summing these raw error give us a misleading picture. It hides how far off we actually are. So what should we do instead? Let's try to make these error positive. So we square the errors. Why? Because squaring them up makes everything positive. So nothing is going to cancel out. And it also emphasizes larger errors more, which makes sense because a bigger mistake should hurt more. We square the error from the first observation. We have -10 whole square 100. We have square of -7 49, square of -3 9, square of 3 as 9, square of 7 as 49, square of 10 as 100. If we add all these squared error, we get 307, and which is a positive quantity. This sum of squared error give us a proper sense of total error. And this is what we'll do. We'll try to minimize the sum of squared error instead of minimizing just the sum of error term. Why? Because sometimes the error can take negative value, sometimes it can take a positive value, and adding those sum of error might cancel out each other and give us value 0. And that would give us a false sense that there is no error. Whereas when we square them up, we have all the positive quantities now, and that would give a proper sense of the total error present in the model. So we started with this null model equation yi is equals to beta naught plus epsilon I, where we have beta naught as one intercept and epsilon I as uncertainty present in the model. Our goal would be to find a value of beta naught that makes the sum of squared error as small as possible. And this method has a proper name. This method of minimizing the sum of squared errors is called the ordinary least square estimation method. Well, in this video, we saw that given only dependent variable and no other independent variables, the best prediction we would have is the sample mean, because the sample mean average is the point that lies in the middle of all the other data points. It is the point that minimizes the total deviation from all the values. But all this is our intuition right now. In the next video, we will see how to prove mathematically that yes, the average sample mean is indeed the best prediction given only dependent variable to us in any data set.